We talked about last week. We're going to finish up talking about chapter 8. And afterwards, if you have any questions, obviously on anything, I'll be more than happy to answer them. And also afterwards as well, I did bring a couple of copies of the exam with the multiple choice questions in case you would like to look those over. And by the way, if you do have questions on anything, you're more than welcome to ask and all that kind of stuff. Okay, so in this chapter, we got through a good majority of the gas stuff last time. Just to remind everybody, we talked about a bunch of different sort of gas laws and sort of relationships last time. We talked about, first off, the kind of common units that we see with gases, which are atmospheres. So 1 atmosphere is equal to 760 millimeters of mercury, and that equals 760 torr. And obviously 760 would be the number that you would use to go between atmospheres and millimeters of mercury, or atmospheres and torr. Obviously, to go between millimeters of mercury and torr, it's a 1-to-1 relationship, so you just basically change the number. We talked about Boyle's law, and Boyle's law is P1V1 equals P2V2. And that is the pressure volume relationship, and this is at constant temperature. And as we talked about, as one goes up, the other goes down, and obviously vice versa there. So as the pressure goes up, the volume goes down, and as the pressure goes down, the volume goes up. We also talked about Charles' law, which is V1 T1 is equal to V2 T2. This is at constant pressure. And remember here, in pretty much all gas laws, temperature does need to be in Kelvin. So that's a 273 plus our temperature in Celsius to do that. And the relationship here is the reason it's able to keep constant pressure is as the temperature increases, the gas molecules should fly around a lot faster, which if the volume did not move, we would see an increase in the pressure. So to stop the increase in pressure, what happens is basically the volume will also increase as well. Gives everybody a lot more room to fly around in, and it keeps the number of collisions relatively constant, and that keeps the pressure also maintaining constantness. Same thing here. If we drop the temperature, our gas molecules will start to fly around a lot slower, which again, if the volume did not adjust, we would see a decrease in the pressure. To fix that, basically the volume will come down in this situation, bringing everybody closer together, which will keep the collisions occurring and keep the pressure constant. And that is opposite of basically what happens in Guy-Lussac's law. And in this one, this is P1 T1 is equal to P2 T2. This is at constant volume. So in this particular case, the volume does not adjust as the temperature changes. So as the temperature increases, gas molecules fly around faster, more collisions, and we do see a rise in the pressure that correlates to that. And opposite is true. If we lower the temperature, everybody's flying around a lot slower, less collisions, and we do start to see a drop in the pressure because of that. In addition, we had our good friend Avogadro, which had a law, and that is V1 over N1 is equal to V2 over N2. This is actually at two relationships. This is at constant temperature and pressure. So in a constant temperature and pressure situation, we have this relationship between V, which is volume, and N, which are moles. Yeah. By the way, again, temperature up here also does need to be in Kelvin. Basically, the relationship is they kind of change proportional. So as the volume goes up, so does the number of moles. And as the volume comes down, so does the number of moles. Kind of putting all these together gave us the gas law I think we saw at the very end last time, which was the ideal gas law, which is PV is equal to nRT. Now, this one is very different, obviously, than all the previous ones. There is no kind of before or after situation. It is just a kind of one and done situation here. It is also the most restrictive in terms of units when you use the ideal gas law. 100% of the time when you use the ideal gas law, pressure needs to be in units of atmospheres. Volume needs to be in units of liters and should be moles. T needs to be Kelvin as the units. And really the reason for all that is R. R is the gas constant 0.08206, and it has units of liters times atmosphere divided by Kelvin times mole. So that's really the reason why everybody else needs to be in those units, is because of the units of the gas constant. Some people do use the rounded version of that number, 0.0821, which is perfectly fine. The also good thing is you're typically always given that, so you'll have the units that go with it. So that also hopefully remind you of what the units for the ideal gas law should be. Now, there's a couple other relationships that we talked about. One was STP. STP stands for standard temperature and pressure. And it actually does represent some values. The temperature is 273 Kelvin and the pressure is 1 atmosphere. So again, if something says this is being done at STP conditions, that is what it means. And there is a relationship that 1 mole of any gas at STP is 22.414 liters. And that's at STP is the only time you can use this relationship. And you can use that relationship in some cases. It will allow you maybe not to have to use the ideal gas law, but it 100% has to be at STP, or you cannot use that relationship. The good news about the ideal gas law is you could do it at STP conditions or any conditions. So if you're worried that maybe you're going to use that incorrectly, just put everything into the ideal gas law and then you'll be fine. Even if it's STP conditions, you just put in 273 for the temperature, 1 atmosphere for the pressure. Also a reminder that in a lot of problems, they don't give you the gas constant in the actual problem. It's just assumed that you know you have that value always available to you if you need it. Good way to work these problems, as we talked about last time as well, is to kind of pull out the information from the problem, label it as a pressure, a volume, or a temperature. And a lot of times that will kind of, you can almost see the gas law in what you pull out of the question, and that'll kind of pull you to the right one, hopefully. Yeah. Any questions on any of that stuff I think we talked about last time? Yeah. Okay, then let's finish up the last little bit here, I think. Maybe, there it is. So we've talked about kind of keeping our one variable constant, but we can maybe have all 3 variables changing at once. And this is what is sometimes referred to as the combined gas law. Sometimes referred to as the combined gas law. And basically we get it by taking basically 2 ideal gas laws and kind of putting them together. And since moles really don't change all that much if you don't open the container, we get P1 V1 over T1 is equal to P2 V2 over T2. Now, the pressure on both sides, it doesn't matter the units as long as they are the same. The volume on both sides, again, does not matter the units as long as they are the same. Just like every other gas law, temperature here, again, does need to be Kelvin when we're using this. I would say this is the one that gives people probably the hardest time rearranging and solving. But again, as we talked about in terms of rearranging, remember that basically you could think of it as almost like a fraction on both sides. And if you move across the equal side, everybody ends up in opposite locations, right? So that's sort of a quick way you can kind of move things around and probably do it correctly. That's basically multiplying and dividing things to the other side. But everybody ends up pretty much in the opposite location of where they started if you move them across the equal sign. So why don't we try one here and see how our rearranging, all that good stuff works. Consider a sample of oxygen gas at 27 degrees Celsius with a volume of 9.55 liters at a pressure of 2.97 atmospheres. If we change the pressure to 8.25 and we heat it to 125, what would be the new volume? So take a few minutes, see what you come up with. Let's take a look. So again, pulling out the information, we got obviously a temperature here that is 27 degrees Celsius. That goes with a volume that is 9.55 liters and a pressure that is 2.97 atmospheres. That is followed by another pressure here of 8.25 and a temperature of 125 degrees Celsius, and we are looking for a volume. So again, just by pulling out the information, that really should lead you to the combined gas law, which again is the only one that really kind of deals with all three of these variables together. We again could just take the first ones in the problem and call them ones. We could take the other guys there and call them twos. In terms of the pressure, they are both atmospheres, which means we're good on terms of the units, but our temperature, much like most, does need to be converted. So we're going to add a 273 to each of these. Gives us 300 Kelvin plus a 273 gets us a 398 Kelvin. So in this particular case, again, P1, V1, T1 is equal to P2, V2, T2. We are looking for V2, which means we really need to move the other two guys to the other side. So again, we're basically multiplying and dividing, but the quick way is T2 is on the bottom. It will end up on top, and P2 is on top. It will end up on the bottom, and that's really a quick way to rearrange it. And that will get you P1, V1, T2 divided by T1, P2 would equal our V2 in this case. Any questions on that there? Again, basically what we're doing is multiplying T2 to both sides, and we're dividing P2 to both sides. That hopefully helps us get everybody in the right location. So up on top should go P1, which is 2.97. Our V1, which is 9.55 liters, and it's going to be actually T2 up on top, which is 398, divided by T1 on the bottom, which is 300, and our P2, which is 8.25 atmospheres. Atmospheres will cancel, the Kelvin will cancel. That is going to leave us just liters left, which is good because we're solving for a volume. That means we're going to take 2.97, we're going to times it by 9.55 and times it by 398, hit equals. We're going to divide it by 300, hit equals, divided by 8.25, hit equals. That is going to give us a volume of 4.56 liters in this particular case. Any questions on the rearranging or any of those things? So again, this one gives people sometimes a very hard time, the rearranging part, and we just want to make sure you get the right temperatures in the right spot. So that's also a very common error. You know, they have the wrong temperature up on top and the other temperature on the bottom and stuff like that. Any questions on that one? Okay.
We do the same thing as long as we...
You would. So we just find a place to scribble on here. That works. So if you had the same equation, P1, V1, T1, and your P2, V2, and T2, and you said you wanted to solve for P2, is that correct? Yeah. So yeah, it would work the same way. So again, sort of the quickest way is this, we need to move V2 to the other side, right? So he's up on top, he will end up on the bottom. The T2 will go to the top. And what that would give you is basically everything on the left stays the same with our T2 coming to the top and our T1 and V2 equals P2. Yep. And now, for example, though, if you were looking to solve for T2, you got a little bit more work to sort of do, because basically in this case, we actually need to get T2 by itself up on top. So since it's on the bottom, you would actually want to move this guy over first, and that would get you P1 V1 T2 over T1 equals P2 V2. Now that you have this guy isolated up on top, you then got to move everybody else back to the other side. And what you would do is, again, P1 and V1 are both on top, so they both will end up back on this side, and our T1 will come back this way. So you'll end up with T2 is P2, V2, T1, and on the bottom would be our P1, V1, and then that will get you the right way. So whatever you're solving for technically needs to be up on top by itself. So in this case, if you were going for T2, it's actually on the bottom. So you got to first move it to the top and then bring everybody back to the other side. And really what we're doing by going cross and stuff, like I said, is really multiplying both things to the other side and dividing, those things to the other side as well. It's basically mathematically what we're doing. Sometimes it's easier just to go, I'll just move it to the opposite location without thinking about kind of the multiplying and dividing part. Any questions on that? Yeah. Yep. Okay, so that is the combined gas law, obviously dealing with everybody there. So the last sort of thing we're going to talk about, I think, in gases here is the idea of partial pressures. And Dalton's law of partial pressure sounds very sort of scary, but it's really not too bad. So if we had a situation, for example, where we had a container and basically the only gas in that container was gas A, as gas A is basically flying around, the total pressure on that container would be all a result basically of the gas A that's flying around. It's really the only gas that's sort of in there. Now, if we ended up with a container where we had gas molecule A flying around, we had gas molecule B flying around, heck, we'll add one more. We have gas molecule C flying around, all in the same container. And that's very commonly how gases come, is they come basically as mixtures of different gases. The total pressure now is a result of not just gas A, the pressure of gas A, but it's also the result of the pressure being applied by gas B, and it's also the pressure applied by gas C. So in a mixture of gases, the total pressure of that mixture is a result of what are referred to as partial pressure. So each of these would be what are referred to as partial pressures, really because they partially make up all the pressure that is there in that system. How do we actually get the sort of partial pressures of each of these gases? Well, one thing that makes something sort of an ideal gas is the idea that different gas molecules, even if they're in sort of the same container in an ideal situation, they're assumed to basically have no interaction with each other. And what that means is, for example, in this example here, we have three different gas molecules all flying around in the same container. Assuming ideal situations, like in the ideal gas law, gas molecule A will have really no interaction with gas molecule B or no interaction with gas molecule C. It's almost like they are in there separately by themselves and not really together. So what that means is we can really figure out the partial pressure of each gas by simply applying the ideal gas law in a lot of situations, where we would solve for P, which would be nRT divided by V, really for each gas. So you would do each gas separately, as we could think of them as being in there kind of by themselves. The good news is, though, because they are all in the same container, that means that the temperature, for example, for all three gases should be the same because they're in the same container in the same room. That also means that the volume should be the same for all the gases because they're in the same container in the same room, which basically means when we look at the ideal gas law here, really the only thing that will sort of be different for the different gases is the number of moles. And R is a constant, obviously. So R is a constant, T and V will be the same for all the gases. So simply all you have to do in a lot of cases is figure out the moles of each of the gases. Once you have the moles, you basically just do an ideal gas law separately for each gas. And then to find the total pressure, you simply add up all the partial pressures together. So you just simply add them together, and that would give you your total pressure in this situation. Any questions on that there? So that's basically what this says. Again, we could just simply do the ideal gas law for each gas separately. And then basically to figure out the total pressure, just add those numbers together to do so. So why don't we try one here, see? So let's say we had 5 grams of helium and 5 grams of neon. They're in a 2.5 liter container at 27 degrees Celsius. Calculate the partial pressures of each gas and the total pressure. Helium on the periodic table is 4.003. And neon on the periodic table is 2018. I'm going to go with. All right, so you should end up with 3 answers here, 2 partial pressures and a total pressure. Okay, so let's see how we're doing. So again, in this case, we basically have both helium and neon flying around the same container. So that definitely tells us we have the mixture of gases, we have some partial pressures happening. If you're not sure maybe where to start, we do have grams, which is not useful in a lot of gas laws, but we definitely know we could take grams to moles, which is useful obviously in a gas law, and that's like N. We obviously have a volume that is 2.50 liters. We have a temperature that is 27 degrees Celsius, and we're looking for some pressures here. So again, you can pretty much get yourself there, hopefully, to the ideal gas law. We're just going to solve really for the ideal gas law for each of the gases separately. So to do that, we do want to first probably convert our grams into moles. So we do that using the molar mass. So for helium, we would take our 5 grams, we would go to the periodic table, and we see that is 4.003 grams per mole for helium, and that gets us 5 divided by 4.003. We'll call it 1.25 moles. We would also, while we're here, do it for neon. So neon was also 5 grams, but we want to obviously use the molar mass here for neon, which is 2018 grams per mole. That gets us 5 divided by 2018, looks like a 0.248 moles. While we're at it, we also need to add a 273 right to our temperature there to get it to Kelvin, which would be 300 Kelvin. Our volume is okay because it is in units of liters, which is what we need for the ideal gas law. So really at this point, we got everything we need to solve. And again, we're just going to do 2 separate ideal gas law calculations where our PV is equal to nRT, solving for P. So bringing this to the opposite side down gets us that the P for the helium here would be nRT divided by V. Putting in our numbers here for helium, it would be 1.25 moles, 0.08206, which is our gas constant that you always have, and our temperature, which is 300 Kelvin, all going to be divided here by our volume of 2.50 liters. Moles cancel, Kelvin cancel, liters cancel. Leaves you just atmospheres left over, which is good because it is a pressure. That's going to be a 1.25 times 0.08206 times the 300 divided by a 2.5, looking like a 12.3 atmospheres. That 12.3 atmospheres would represent the partial pressure of helium in this case. So that is the partial pressure of helium. Any questions on that so far? We're also obviously interested in the partial pressure of neon, which basically is the exact same calculation. The only difference is we want to use neon's moles. So the partial pressure of neon should also equal nRT divided by V. Here again, as I just mentioned, we want to use the actual moles for neon, which would be 0.248 moles. Our gas constant still again the same. Our temperature is the same because it's in the same container. And obviously our volume is the same because it's in the same container. Taking our 0.248 times 0.08206 times the 300 and divided by a 2.5er gives us a 2.44 atmospheres. That would be what is known as the partial pressure for neon in this case. First off, any questions on any part of that calculation? Really just an ideal gas law like we talked about previously. Again, we just call these partial pressures because they're both in the same container. They're both contributing to the overall pressure. The total pressure can be found by doing what? The total pressure here would be the partial pressure of helium plus the partial pressure of neon, which means we simply just need to add both of those numbers together. That is 12.3 atmospheres plus a 2.44 atmospheres. And that gets us something in the ballpark of 14.7 atmospheres would be the total pressure of this mixture. Which gas is supplying the most of the pressure? It is helium. Any ideas why helium is supplying most of the pressure? What would you think? It actually has to do with up here. The molar mass of helium is 4. The molar mass of neon is 20. Helium is a much lighter gas. Lighter gases will be moving much faster. So helium is zipping around because it's much lighter. It will have a faster velocity because it's able to fly around a lot faster. It's causing more collisions, and more collisions contributing to more pressure in that mixture. So usually the lighter gas is flying around in a mixture is usually the one that's causing probably most of the pressure because it is moving much faster than helium or neon in this case, which is moving a lot slower. Any questions on that there? Questions on this type of partial pressure? Basically an ideal gas law separate for each gas, add each of the pressures together at the end. So that is one common sort of ideal gas or partial pressure situation. This is another one. This is probably like the experiment you did, a little potassium chlorate plus some manganese dioxide as the catalyst. And if you did that, did you do this experiment with the twistle tube? It was on the handout, yeah. Worst experiment ever. That's why I don't go back to lab. They had the twistle tube still, the big, the little skinny tubes that break. Yeah. I had one break in my hand once. All right. So what you probably learned was if you didn't dump enough of that in there, it was a very long night for you. Yes, which was the catalyst. So if you didn't dump enough of that. But as you heated this basically went through a decomposition reaction to KCl plus a little bit of O2. And basically the O2 here had nowhere to go. So it went down through here, through the tube. You had a container filled with water. And as the gas comes in, the water bubbles out, right? And you're left with this empty spot here, right? And that empty spot is really not empty. That is in this example where the oxygen gas basically ended up. But when we collected the gas, we actually collected it with water involved here. And when a reaction happens, there's heat. And heat in reaction with water means that water will start to evaporate. So in this situation, what ends up happening is we do collect the oxygen gas, which is really the purpose of the experiment. But as sort of a side product of doing the experiment this way with water involved, we actually get some water vapor that actually comes along for the ride. And it creates really a partial pressure situation where the total pressure is the pressure of the gas you're really interested in. plus the vapor pressure of water. We usually need to do a correction in an experiment like this because we're not really interested in the pressure associated with the water part of it. We're really just interested in the pressure of the gas that we were trying to collect. So we could find that by simply rearranging that the pressure of the gas we're interested in would be the total pressure minus the vapor pressure of water. That is the vapor pressure of water, which is typically a value that you look up on a table based off of temperature. The total pressure in a laboratory situation is what you get from the barometer reading. It's basically the room pressure. And we do this sort of correction where it's sometimes referred to as getting the pressure of the dry gas because we're kind of subtracting off the water component from it. And so it really is a partial pressure situation. Easy way to sort of figure out the pressure of the gas, which is what you're interested in, is ending up just really subtracting off the water vapor from it. So if we look at a problem like that, a sample of oxygen gas was saturated with water vapor. So those are the key words that you know it is this type of situation. It will sometimes say it was saturated with water vapor. It will sometimes say it was collected over water. Some type of mention of collecting a gas with water involved means that you're going to end up with this situation where you get the gas you want, but you also get water vapor involved. So usually you need to do this correction. The total pressure is 753 torr. The vapor pressure of water at 30 degrees, which is when this was a run, is 31.84. So in this particular case, the total pressure, as we just mentioned, is the pressure of the oxygen gas plus the vapor pressure of water. So again, if we were doing this experiment, we definitely would be interested in just the vapor pressure of water, or the pressure of water. I'm sorry, the pressure of oxygen. And to find the pressure of oxygen, it would be the total pressure minus the vapor pressure of water. The total pressure they gave us, which was 753 torr. The value of the vapor pressure of water, this would be a value you would find on a table, which would be minus 31.824 torr. That tells us that correcting for the vapor pressure of water, the actual pressure contributed by just the oxygen gas would be 721, I'll round it there, torr in this case. So we subtracted off really the contribution to the pressure associated with the water, which is really what we're not interested in, leaving us really the pressure of what we are interested in, which is the pressure of the oxygen. In this case, if we wanted to convert it to atmospheres, this is where our 760 number would come into play. 760 torr is an atmosphere, which means we will end up with .949 atmospheres would be the partial pressure of oxygen in this case. And this is a very common sort of experimental way that we end up with sort of a partial pressure situation where we sort of collect that water vapor as a result of really just doing the experiment the way that we did the experiment. And we're not, again, usually interested in the water. So we have to do, it's really oftentimes thought of as like a correction factor there to kind of correct out the water vapor pressure so that we could get to the gas pressure that we're actually interested in. So this is another very common sort of partial pressure situation. Any questions on that? It would actually just be this formula here, that the total pressure is equal to the partial pressure of the gas you're interested in. So just happens to be O2 in our case, but really the gas you're interested in plus the vapor pressure of water. And you would use this sort of formula, if you will, which was, I think, what I wrote here, basically. You would use this formula anytime. Again, those are really the key words that you oftentimes will see in a problem. It will say, like it did in the last one, saturated with water vapor or collected over water. So again, some mention of collecting a gas in water being involved. And it's really a situation like you did in lab where you use water and you displace the water will always result where you usually will have to do this calculation here to get yourself to figuring out the pressure of just the gas by itself. The good news is it's really just a subtraction thing. You're going to subtract off the water vapor from the total pressure. Other questions on that? All right, so to finish up, the kinetic molecular theory of gases are, some of the stuff that we've talked about. Gases are tiny particles. They're atoms or molecules. These particles are small compared to the distances between them. So the volume of the actual gas molecules can assume to be zero or negligible. This is really number two here. Really what we are talking about when we talk about an ideal gas is we assume that the volume of the gas molecule itself is relatively small compared to the container at which it's flying around in. So that's why if you think about a lot of gas problems that you come across, a lot of times they'll talk about the gas, the volume of the container rather than the actual volume of the gas itself. So in ideal situations, the container's volume is much more larger than the actual small volume of the gas itself. The particles are in constant motion, colliding with the walls of the container. This is what causes the pressure. Number four is the second thing that really makes something an ideal gas, and why, as we just talked about with partial pressures, even though we have a whole bunch of gases in the same container, we could do the ideal gas law separately for each of them, as they are not really interacting with each other. And it's assumed that the particles don't attract or repel each other. Why is that important? Well, if there actually was some attractive forces between the different molecules of gases, what causes pressure is as the gas is flying around, it hits the container, which means if this gas molecule is flying around and there's another one that is attracted to it, it's going to kind of pull it away from hitting the container, and it would cause a change in pressure that you might see in that situation. So in these ideal situations, we just assume that they're not interacting with each other, and we don't have that situation occurs. If you ever take another chemistry class, you might talk about gases, which are sometimes considered real gases. In that situations, you do have to take that into account, but those really only occur at really high pressures and really large temperatures. But under normal pressure and temperature conditions, most gases will behave in sort of an ideal situation. And that's why we sort of consider most gases sort of ideal. The average kinetic energy of a gas is directly proportional to the temperature. So obviously as the temperature increases, the gas molecules fly around faster. And obviously as it lowers the temperature, they do fly around lower as well. And that brought us to some of the relationships that we talked about. Again, at high temperature, gas particles moving faster, more collisions. We would expect to see the pressure start to increase, especially where the volume doesn't adjust, as we talked about. And at lower temperatures, we would start to see hopefully a pressure start to decrease as those volumes maybe don't adjust. And that definitely is what happens in that rigid container. Rigid means that basically it's locked into place, nothing's moving in terms of the volume. And we would see those increases and decreases in pressure based on temperature. That was basically our Guy-Lussac's law, P1 over T1 equals P2 over T2 with the fixed volume. We see the rise in the pressure as the temperature increases and decrease in the pressure as the temperature decreases. Same thing with Charles' law. Again, we're able to maintain that constant pressure by the volume basically adjusting to keep the collisions relatively constant as well. That is gases. Yes. Any questions on gases or anything like that?